What if I told you that the most flown commercial aircraft in history was originally considered too small, too underpowered, and too risky to ever compete? Ladies and gentlemen, welcome to Moves and Flies, and today we are diving deep into the machine that literally changed the world of aviation forever. This is the Boeing 737. From its controversial birth in 1967, through 4 generations of radical engineering, all the way to the disasters that shook the entire aviation industry, we are covering all of it. Buckle up. This is going to be a flight you won't forget. The year is 1964. Boeing is already dominating long-haul aviation with the 707 and racing ahead with the 727. But there's a critical gap in the market: short-haul, high-frequency routes between smaller cities. Airlines were still flying propeller-driven aircraft, like the Fokker F-27 and the Douglas DC-3 on these routes, burning money on inefficient operations. Lufthansa, yes, the German carrier, approaches Boeing with a bold request: build us a small, twin-engine jet that can operate from shorter runways, carry around 100 passengers, and keep operating costs low. Boeing's engineers, led by Jack Steiner, take on the challenge. But here's the twist: United Airlines, one of Boeing's biggest customers, refuses to order the aircraft unless Boeing makes it bigger, capable of carrying up to 130 passengers. So right from the start, the 737 is born out of a compromise, a machine that needs to be small and big at the same time. This engineering contradiction will shape every single decision made about this aircraft for the next 6 decades. In April 1965, Boeing officially launches the 737 program, and the engineering decisions made right here, in this moment, will haunt and define the aircraft forever. Let's start with the most iconic feature of the 737, its engines. Boeing chose the Pratt & Whitney JT8D turbofan, the same engine used on the 727. Sounds logical, right? Reuse existing technology, reduce costs. But here's the problem. The 727 mounts its engines at the tail. The 737 was designed with engines mounted under the wings, which is more aerodynamically efficient and better for weight distribution. The catch? The JT8D is enormous, and the 737 is designed to operate from airports with minimal ground support, meaning the aircraft needs to be low to the ground for easy boarding without jet bridges. The result? Boeing engineers had to flatten the bottom of the engine nacelle, creating the distinctive D-shaped engine profile that 737 pilots and mechanics know immediately. The engine is so close to the ground that the accessory gearbox, normally mounted at the bottom of the engine, had to be repositioned to the side. This will matter enormously decades later. The 737-100 enters service with Lufthansa on February 10, 1968. It carries 85 to 103 passengers, powered by 2 JT8D7 engines, producing 14,000 pounds of thrust each. But the 100 is almost immediately overshadowed. United Airlines pushes for the stretched version, the 737-200, just 1.83 meters longer, but with significantly more passenger capacity, up to 136 seats, and much better range. The 200 becomes the real commercial success, with over 1,144 units built. It also introduces the first of many 737 innovations: a self-contained air stair built into the forward door, allowing operations at airports with absolutely no ground infrastructure. Remote outposts, jungle airstrips, gravel runways, the 737-200 could go where no jet had gone before. By the late 1970s, the aviation world is changing fast. The oil crisis has made fuel efficiency the #1 priority for every airline on Earth. Competitors like Airbus are launching the A320 with brand new CFM56 engines that are dramatically more fuel efficient than anything on the 737. Boeing faces a critical choice: design a completely new aircraft or evolve the 737. They choose evolution. And this decision creates one of the most remarkable engineering challenges in commercial aviation history? The solution is the 737 Classic Series, the -300, -400, and -500, introduced between 1984 and 1987. The key upgrade, replacing the old JT8D engines with the modern CFM56-3 high bypass turbofan. This engine is wider, more powerful, and incomparably more fuel efficient, producing up to 22,000 pounds of thrust on the -400 variant. But here's the brutal engineering reality. The CFM56's fan diameter of 60 inches simply cannot fit under the 737's low wing with the standard underwing position. Remember that D-shaped nacelle? Boeing engineers now had to go even further. They moved the engine forward and upward relative to the wing, repositioning it ahead of the leading edge, and flattened the nacelle even more aggressively. The result is an engine installation unique in commercial aviation. The front of the engine sits above the center line of the wing attachment, with the accessory gearbox still on the side. This non-standard geometry changes the aerodynamic interaction between the engine and the wing significantly. Boeing's engineers compensate with careful computational fluid dynamics modeling, remarkable for the era. The 737-300 enters service with US Air in 1984 and is an immediate commercial hit. It carries 128 to 149 passengers, has a range of approximately 4,400 kilometers, and reduces fuel burn by nearly 25% compared to the -200. The -400 stretches the fuselage by 3.05 meters, pushing capacity to 168 passengers, ideal for high-density short routes. The -500 goes the other direction, a shrink version, essentially a modern re-engine of the original -100 concept, perfect for thinner routes. Combined, the Classic Series generates over 1,988 orders and cements the 737 as the backbone of short and medium-haul aviation globally. The early 1990s bring a new aviation war. Airbus launches the A320 family with fly-by-wire controls, advanced avionics, and a cabin so wide it feels like a different category of aircraft. Airlines are placing massive orders. Boeing is losing ground. The answer comes in 1993. The 737 Next Generation program. This is not a simple upgrade. This is a near-complete redesign of everything except the basic fuselage cross-section and the fundamental low-to-ground layout. Let's go system by system. Wing. The 737 NG gets an entirely new wing. The span increases from 28.6 meters to 34.3 meters. The wing area grows by 25%. New winglet technology is introduced. Initially optional, later standard, reducing induced drag by approximately 5%, improving range and fuel efficiency dramatically. The new wing also allows significantly more fuel capacity, up to 26,020 liters, enabling transcontinental routes. Engines. The CFM56-7B replaces the -3 series. This engine features a dual annular combustor, reducing NOx emissions by 40% compared to its predecessor, while delivering better specific fuel consumption. The -7B-27 variant produces 27,300 pounds of thrust, making the 737-900ER one of the most capable single-aisle aircraft of its era. Avionics. The cockpit is completely redesigned. Out go the analog gauges of the Classic. In come 6 large liquid crystal displays in the Honeywell or Rockwell Collins integrated avionics suite. The flight management system receives GPS integration for the first time on a 737. Fuselage. The -800 variant, the best seller of the NG family, stretches to 39.5 meters, carrying 162 to 189 passengers with a range of 5,765 kilometers. This is now firmly a medium-haul aircraft, connecting city pairs that a 737 had never been able to reach. Southwest Airlines alone would eventually operate over 750 737 NG aircraft. The NG family generates an extraordinary 6,800 orders, solidifying the 737 as not just a success, but the defining commercial aircraft of the 20th and early 21st century. And now we arrive at the most technically complex and consequential chapter in 737 history, the Boeing 737 MAX. Understanding what went wrong requires understanding the exact engineering constraints we have been building throughout this entire video. By 2011, Airbus launches the A320neo, the new engine option, fitted with CFM LEAP or Pratt & Whitney PW1000G geared turbofan engines. These engines offer 15 to 20% better fuel economy than anything currently flying. Airlines immediately want them. American Airlines, historically a Boeing exclusive customer, signals it will order the Airbus if Boeing doesn't respond. Boeing faces the same crossroads again: new aircraft or evolved 737. Developing an all-new aircraft takes 10 to 12 years and costs upwards of $20 billion. Boeing chooses evolution. Again. The result is the 737 MAX. The chosen engine, CFM LEAP 1B, with a fan diameter of 69.4 inches, significantly larger than the 60-inch CFM 56-7B on the NG. Remember the fundamental problem. The 737 sits low to the ground. With an engine fan diameter of 69.4 inches, Boeing cannot hang the engine in the standard position without it striking the runway. The solution: move the engine even further forward and upward relative to the wing, more aggressively than even the classic to NG transition. The engine nacelle centerline ends up approximately 116 centimeters ahead of the wing leading edge. This creates a measurable aerodynamic effect. At high angles of attack, the engine nacelle generates additional lift on the forward section of the aircraft, pitching the nose up when the aircraft is already nose high. In simple terms, the aircraft wants to pitch up more than it should at critical phases of flight, which can lead to a stall. Boeing's engineering solution is the Maneuvering Characteristics Augmentation System, MCAS. MCAS is a software algorithm that reads data from angle of attack sensors and automatically deflects the horizontal stabilizer nose down to counteract the pitch-up tendency caused by the engine position. On the MAX 8 as originally certified, MCAS could deflect the stabilizer up to 2.5 degrees, a moderate authority. But during the final stages of certification, test data showed the pitch-up tendency was stronger than expected. MCAS engineers increased MCAS authority to 4 times its original specification, up to 10 degrees of stabilizer deflection, without returning the aircraft to the full FAA certification review process. Critically, MCAS relied on data from a single angle of attack sensor, with no cross-check from the second sensor. If that single sensor malfunctioned and fed incorrect data, MCAS would activate without any valid reason, repeatedly pushing the nose down, and the flight crew had a limited number of stabilizer cutout procedures to respond. On October 29, 2018, Lion Air Flight 610. On March 10, 2019, Ethiopian Airlines Flight 302. 346 people lost their lives across both accidents. MCAS activated in both cases due to erroneous AOA sensor data. The 737 MAX was grounded worldwide for 20 months, the longest grounding of a commercial aircraft in history.
The return of the 737 MAX to service was not simply a software patch. It was one of the most scrutinized aircraft recertification processes in the history of aviation regulation. Let's examine what actually changed. First, MCAS authority was permanently limited to a maximum of 2.5 degrees of stabilizer deflection per activation, a hard limit that cannot be exceeded regardless of sensor data. Second, MCAS now requires both angle of attack sensors to agree before it activates. If the two sensors disagree by more than 10 degrees, MCAS is automatically inhibited and a cockpit alert is triggered. Third, pilots received mandatory simulator training specifically addressing runaway stabilizer scenarios, training that was absent during the original MAX certification because Boeing had argued the system was so minor it didn't require additional pilot training. Boeing paid $2.5 billion in settlements and criminal charges. The FAA underwent its deepest institutional reform in decades. The Office of Aviation Safety now has direct reporting lines that remove the potential for certification pressure from commercial interests. The MAX returned to commercial service in November 2020 in the United States. As of 2024, over 900 MAX aircraft have been delivered, and the type has accumulated over 3 million flight hours. The Boeing 737 MAX 10, the largest variant, carrying up to 230 passengers, was still awaiting final FAA type certificate approval as of mid-2024. The saga of the MAX is not a story of a bad airplane. It is a story of what happens when institutional pressure, cost constraints, and legacy design limitations converge without adequate checks and balances.
So what does the full picture look like today? The Boeing 737 family, across all its generations, has accumulated numbers that are genuinely staggering from an aviation engineering standpoint. Over 10,000 aircraft built across all variants. Approximately 1.5 billion passengers carried every single year on a 737. At any given moment, there are statistically more than 1,250 737s airborne simultaneously somewhere on Earth. The 737 has flown to every continent, operated by over 500 airlines, and logged well over 500 million flight hours in its operational history. From a structural engineering perspective, the 737 airframe has proven extraordinarily durable. The basic fuselage cross-section, a 148-inch diameter pressure vessel, has remained fundamentally unchanged for over 57 years. Modern 737s use aluminum-lithium alloys and advanced composite materials for secondary structures, but the primary pressure fuselage remains a testament to the original structural engineering of the 1960s team. The 737's contribution to aviation safety data is unparalleled. The sheer volume of operational data has helped define global standards for fatigue testing, pressure cycle limits, and structural inspection intervals for narrow-body aircraft. Looking ahead, Boeing faces a genuine crossroads. The new midsize aircraft, internally called NMA or 797, was a proposed clean-sheet design to eventually replace the 737 and fill the market gap between single-aisle and wide-body aircraft. That program has been repeatedly delayed. Meanwhile, the A320 family now outsells the 737 MAX in new orders. The 737 MAX 7 and MAX 10 are still navigating certification processes. Boeing's future strategy for single-aisle aircraft is one of the most closely watched decisions in global aerospace. But here is the remarkable truth. A 57-year-old design concept, born from a compromise between a German airline and an American carrier, shaped by the physical constraints of low airport infrastructure, continuously evolved through 4 generations of engineering ingenuity, still operates at the absolute frontier of commercial aviation efficiency and economics. That is not just engineering. That is legacy.
And there you have it, the Boeing 737, from Lufthansa's humble request in 1964 to the most produced commercial jetliner in aviation history. If there is one lesson this aircraft teaches us, it is that engineering is never done in isolation. Every decision has a consequence, every constraint shapes a solution, and every solution creates a new set of constraints for the next generation of engineers to solve. The 737 is not a perfect machine, but it is perhaps the most persistent one. If you loved this deep dive, hit that subscribe button and leave us a comment. What do you want us to break down next? The Airbus A320? The DC-3? The story of the turbofan engine itself? We read every comment. This has been Moves and Flies, and we'll see you at the gate.